So in our previous chapters, whenever a force acted on a particle, we saw that the effect of the force was to accelerate the particle or the object that it's acting on. And we know very well the relationship between force and the acceleration that it produces. Net force equals mass times acceleration. In this chapter, we are going to consider a different effect that a force can have on a system. A force can also rotate a system. The rotating effect or the turning effect of a force is called the torque. And that is the first concept that we're going to focus on in chapter 10. Okay, now let's start with a simple example. Suppose you have to turn the nut shown here and using the wrench, right? And let's say that you have to turn this nut, your life depends on it, right? I allow you to choose between three different forces that you can apply on the wrench. That you can apply, not necessarily on the wrench. One of them is this force indicated by the green arrow, large force indicated by the green arrow, that acts on the nut. The second is a force in 17 Newton force shown by the red arrow, and the third one is another 17 Newton force indicated by the blue arrow. Which of these do you think has the greatest turning effect on the nut? So I'll let you think about this for a moment. You can feel free to pause the video if necessary. If you think about it carefully and ask yourself what you would have done if you had to turn this wrench, you would probably have picked the 17 Newton force, which is indicated with the blue arrow. Clearly that force has the greatest turning effect on the wrench. And that is correct. The force that will have the most turning effect on the wrench would be the 17 Newton force. Now, this shows you that the turning effect of a force does not just depend on the magnitude of the force. It depends on three things actually. It depends on the magnitude of the force, it depends on how far from the rotation axis the force is being applied, and also it depends on what direction the force is acting. So if I had chosen to apply a 17 Newton force somewhere over here, that would not have been as effective as the 17 Newton force, which is far out at 25 centimeters from the axis, right? And if I had applied a 17 Newton force right here, right passing through the axis, that would not have had any turning effect at all, right? And on the same, also, if I apply a 17 Newton force, so the red arrow is a 17 Newton force that is being applied far away from the axis, but since it makes a 37-degree angle, it does not quite have the same turning effect as a 17 Newton force, which makes a 90-degree angle with the wrench, right? So the three factors which determine the torque are the magnitude of the force, how far from the rotation axis the force is applied, and what direction the force is acting in. Okay, now all three of these factors are neatly summarized by a simple formula. And so that formula is the following. It's on the next slide. So torque, which is indicated by the symbol tau, is equal to the cross product of R and F. Okay, for now, let's just focus on the magnitude of the torque. So the magnitude of the torque is simply Rf sine theta, and this formula comes straight from chapter 1. You know what the formula for the magnitude of a cross product is, and that's exactly what we're doing here. So let's look at an example. Suppose you have to, let's just stick with the example of a wrench. So suppose I have this wrench, and I'll just draw a nut over here. Okay, and I'm applying a force at the edge of the handle of the nut, so somewhere over of the wrench. So my force is somewhere over here, and I'm indicating the force with this vector arrow. How would I find the torque of the force? Now, first of all, whenever you're measuring the torque, you need to measure it with respect to some reference point. In this chapter, the reference point will always be the axis, on the axis of rotation. So the axis of rotation of this whole system is an imaginary line which is passing through the center of the nut. So I'm just going to call that O. Let's write the O over here. So the axis of rotation is this point about which the system is rotating. Okay, so how do you find the torque of F about this point? So what you do is you first have to draw the R vector, which is a line which starts from the reference point, which is just the axis of rotation, and goes out to the point of application of the force. So please make sure that you fully understand what the R vector is. It's a vector which originates at the axis of rotation and goes out to the point where the force is being applied. Then you calculate the cross product. Once you have the R vector, you can easily find the angle between these two. So let's call this angle theta. And so the torque would just be the magnitude of R, which is just the length of R, multiplied by the magnitude of the force, multiplied by sine of the angle between R and F. Now you might say that shouldn't it be this angle? Absolutely, you can use that angle if you like, but for a cross product it doesn't really matter whether you use the acute angle or the obtuse angle, because sine of theta is the same thing as sine of pi minus theta. So we have this nifty trig identity that sine theta is equal to sine of pi minus theta. So it's just convenient to work with the acute angle when you're calculating a torque. All right, so that is our formula for torque. And here it's very, very important that you understand the meaning of R. So please pause the video and make sure that you understand it if necessary. We are going, there's another R coming very soon. So it's very important that you understand what this R stands for. Okay, so R, once again to repeat myself, R is a vector that originates at the reference point about which the torque is being calculated, which, as I said in this chapter, is just the axis of rotation. And it terminates at the point where the force is being applied. Okay. Now, this formula can be written in a slightly different way. So, suppose I make this geometric construction, and for that, let me just remove this RF sine theta from here. Suppose I do the following. Suppose I draw a line through the force. All right, and then from the reference point, which is the axis of rotation, I make a perpendicular to this line. So I draw this perpendicular so that this is 90 degrees. Okay, now from geometry, can you tell me what the length of this green line is going to be? The length of this green line would simply be r sine theta, right? So the torque can be written as the torque was Rf sine theta. So the torque is simply r sine theta multiplied by f. It doesn't matter what order I multiply them in. And this particular, so you can see that r sine theta is my green line that I just drew, right? There is a name for this particular length. It's called the lever arm, or r perpendicular. So the torque is also equal to r perpendicular multiplied by f. And what is r perpendicular? R perpendicular is the lever arm. It also has another name. It's also called the moment arm. Okay, let's just quickly review how to find the lever arm or the moment arm. It should be fairly obvious. It's not complicated at all. So let's take another example. So suppose I have this rod which can freely pivot around this point O. And let's say that I'm applying a force maybe in this direction. That is my force, and I'm applying the force over here. My question is identify R and identify R perpendicular, right? So how do we identify R? R would simply be the vector that goes from the reference point out to the point of application of the force. So this is my R vector. And so if I wanted to find the torque using the R vector, I would just do torque equals R times F times sine theta, where this angle is theta, right? Now, if I wanted to find the lever arm, let's do that. So finding the lever arm, it's just a simple geometric construction. The first thing that you do is you draw a line through the force. The next step is to make a perpendicular from the reference point down to that line. So this perpendicular. And this is your lever arm, R perpendicular. Green line is your lever arm. So if you wanted to find the torque using the lever arm, it would just be the force multiplied by the lever arm. Okay. So these are two formulas which give you the magnitude of the torque. And once again, please be absolutely clear about what is R and what is R perpendicular. All right. Okay, now let's talk a little bit about how you calculate the torque in problems. So I have this slide over here. So the first thing that you do when you calculate the torque is you identify the force that's causing the torque. You identify the reference point about which the torque is being calculated. So these are the first two things that you look for. What is the reference point about which I'm calculating the torque? And what is the force whose torque I'm calculating, right? The next step is try to spot the lever arm for that particular force, right? If the lever arm is something that's given, or if it's easy to calculate, then just use the formula torque is equal to lever arm multiplied by force. And that's usually the easiest way to find the torque, as lever arm multiplied by force. Okay, now you might be able to draw the lever arm, but the problem might not immediately give you information about how long that lever arm is, or it might take, you might think that you can find out how long the lever arm is, but you'll have to do some SOHCAHTOA and trig and all that stuff. If the lever arm is not obvious, then it's not worth trying to figure out what the lever arm is. We already have a trig ready formula, which is the formula RF sine theta. So if the lever arm is not is not given or is not immediately obvious, just switch to the other formula, RF sine theta, to find the torque. Okay, so that's the general strategy that you use to calculate torque. Right? Okay, now I'm just going to briefly talk about one more thing here, which is the direction of the torque. Okay, so let's go back to our drawing here. So you might have noticed that the torque is a vector. So torque is R cross F if you write the full vector form. Now from chapter 1, you know how to calculate the direction of a cross product, right? So feel free to pause the video and see if you can figure out the direction of the torque in the diagram on this page. So R points in this diagonal direction, F points to the left. So if you use the right hand rule, you would point the four fingers. You would have your right hand with the four fingers pointing one way and the thumb pointing in the opposite, thumb pointing perpendicular to them. And then you would point the four fingers of your right hand in the direction of R, and then you would curl your fingers in the direction of F, and your thumb would give you the direction of the torque, which in this case would be out of the board, right? So the torque here is out of the board. However, and so that's the direction of the torque vector. In this chapter and also in the next chapter, we are not really going to bother with the actual direction of the torque vector. We are simply going to, it's enough for our purposes to just keep track of whether a certain torque is a counterclockwise torque or a clockwise torque, right? What does that mean? Counterclockwise versus clockwise torque? Okay, just ask yourself, what is the force F trying to do to the object relative to the fixed point O, right? Which way is it trying to rotate the object? Clearly, the force F, if it has its way, it's going to rotate this beam in the counterclockwise direction, right? And so we would call this torque, call this torque a counterclockwise torque. CCW, I just mean counterclockwise. It's my shorthand for counterclockwise. Okay, let's say that I have another force which is acting somewhere over here. Suppose I have another force, F1, which is acting over here. Is F1 a clockwise or a counterclockwise? Is it exerting a clockwise or a counterclockwise torque? Let's think about that. I forgot to put the vector arrow here. All right, so my question is this red force arrow F1, is it exerting a clockwise or a counterclockwise torque? The answer is it's exerting a clockwise torque. Why is that? Because if F1 has its way, right, forget about all the other forces. Just think about F1 and just think about the reference point O. So if F1 had its way, then it would rotate the beam clockwise about O, right? And so that tells us that F1 is exerting a clockwise torque. So in doing problems in this chapter and the next chapter, it's enough to just keep track of which torque is clockwise and which torque is counterclockwise. We don't really need the actual direction of the torque vector for the elementary problems in this course. Okay. So that's the direction of the torque. Let's look at an example of applying the torque formulas. So the torque formulas that we just saw were torque equals R cross F. That's the most general formula, R cross F, which can be written as the magnitude of the torque. Remember that if you don't put the vector arrow, it just means magnitude of that vector. Magnitude of the torque is Rf sine theta, which can also be written as force multiplied by lever arm times the force, right? So let's look at an example of calculating the torque. I'm going to do one example here, and there's also a nice example on slide 8 of the PowerPoint. I think we'll also work through that one. So so the example that I'm considering is this one. Suppose you have this triangular object which is standing on the ground, and let's say that this distance is 10 meters, and let's say that you're exerting a force of 3 newtons at the top of the triangle, and that force is horizontal, so it's parallel to the ground. What is the torque of this force about the point O? So if the object is fixed at O, right, then when you apply this force, at the top, the object is going to topple over about the point O, right? So this force of this 3 Newton force will exert a torque about the point O, right? The axis of rotation is passing through the point O and is perpendicular to the plane of the paper. So the question is, what is the torque of 3 Newton's force about O? Well, how would you answer it? So if you go back to slide 6, which sort of gives you the set of steps that you mentally follow in calculating the torque, identify the force and identify the reference point. So the force is 3 newtons. We can clearly see that. The reference point is O, so we are completely clear about these two. The next step is to try force multiplied by lever arm. So we want to find the lever arm of the 3 Newton force. How do we do that? So finding the lever arm is just a simple geometry construction. We draw a line through the force like this, and then we make a perpendicular from the reference point out to that line. So this is going to be our lever arm, right? This angle is 90 degrees. Okay, so the next thing we want to consider is do we know the length of this lever arm right away? The answer is yes. Clearly it will just be 10 meters. So then we found the lever arm, we already know the force, so we can easily find the torque as torque is equal to lever arm multiplied by force, which is 30 Newton meters. Okay, one brief comment about the unit of torque. You might have, can you tell me what is newtons times meters? Have you seen this combination before? The answer is yes. When we talked about work was force times distance, so that was also newtons times meters, and that particular combination was called a joule. However, joule is a unit for energy, and torque is a completely different quantity. So torque should not be measured in energy units. So even though dimensionally it's equivalent to energy, right? It does not make sense to measure torque in joules. And so that's why when you're talking about a torque, the unit is just Newton meters. You don't call it joules, right? So torque is always just Newton meters, right? So dimensionally it happens to be the same dimensions as energy or work, but it does not make sense to use the same units for energy as torque because they're fundamentally different quantities. All right, so that is how we found the torque in this case. Notice that if you had tried to use the other formula Rf sine theta, what would the R have been? The R would just be, the R would be the vector which starts at O and goes out to the point of application of the force. So that would have been one of the sides of this isosceles triangle. This would have been your R, right? And then you would have needed to know the angle between R and F, which is this angle. And so if you wanted to use that method, you would have had to do some geometry, some SOHCAHTOA and all that to figure out the angles and the length of R and all of that stuff. And if you do that, you'd get exactly the same answer. But we didn't need to do that because the lever arm was obvious. So in problems where the lever arm is obvious, just go ahead and use force multiplied by lever arm to find the torque. Okay, we're going to do another example, and that's the example on slide 8. Okay, so in this example, we have a light rod which pivots freely about its left end, and so you have a fulcrum here. Fulcrum just means that it's a point where the end of the rod is fixed and it can freely pivot around that point. And you have an object that's placed at a distance d from the left end of the rod. So the object is over here. This distance is called d, right? And you're given the angle that the rod makes with the horizontal. So this angle is 30 degrees. I'm just going to call this angle phi for now. Okay. And we have to find the torque exerted by the load. The load just means the weight of this heavy object that's placed on the rod. So that's going to be mg. So we need to find the torque exerted by mg, and we also need to find the torque exerted by F at the end of the rod, right? Okay, so we have to calculate two torques. All right, actually, yeah, we have to calculate two torques and then also find the magnitude of F. Okay, so let's start with the torque due to mg. Now, if you go back to slide 6, which gives you the series of mental steps that you follow when calculating the torque, you know that your first attempt should be to use the formula torque equals force multiplied by lever arm, right? And for that, you want to see if the lever arm is something that you can easily spot, right? So how do you find the lever arm of mg? First thing that you do is just draw a line through mg, which is not that important. It's not necessary in this case. And then you draw a perpendicular from the reference point down to that line. This angle is 90 degrees. Okay. This distance is the lever arm, our perpendicular, right? Do we know what the length of our perpendicular is? We're given the d, but we really don't know what our perpendicular is. We can find it if using SOHCAHTOA, but if you need to do SOHCAHTOA, then you might as well just use the other formula because that's already trig ready. So the other formula for torque is Rf sine theta. Okay, so R would be this vector. This is our R vector. And make sure you understand why I'm calling this as R. R is a vector which starts from the reference point and goes out to the point of application of the force. So the reference point is the axis of rotation here, O, and let's just call this point as O. And so R is the vector that starts at O and goes out to the point of application of the force. And the length of R here is clearly d. Right? Rf sine theta. What is the theta? Theta is the acute angle between the force and the R vector. So theta is this angle, right? What is the value of theta? Theta is clearly 60 degrees in this case. So what is the value of the torque? So the torque would be Rf sine theta. So that's going to be 0.45 multiplied by mg. M is 100, g is 9.8. So 100 times 9.8. That's the F times sine of 60 degrees. And if you work that out, you should get 382 Newton meters. Okay, so that is the torque exerted by mg about the point O, right? What about the torque exerted by F? So let's run through the same steps. So the first thing that you want to do is identify the force and the reference point. Those are really clear. Next thing is you want to try R perpendicular times F. So let's draw the R perpendicular. So you would just draw a line through the force and then make a perpendicular from the reference point to that line, and that just turns out to be the length of our length of this rod, right? So we found the lever arm, and so the lever arm is just the length of the rod, and so the torque would just be the length of the rod itself, which is 1.5 meters, multiplied by the force, F. And so we can only get the answer in terms of F so far. So it's just going to be 1.5 F Newton meters would be the torque, right? Okay. The last question is asking us to find the magnitude of F. Now, the rod is at rest. We're going to learn in the next chapter that when an object is at rest, if it's at rest indefinitely, not just at rest for one moment, but if it's at rest indefinitely, then all the torques on it balance out and all the forces on it balance out as well. And that's pretty much the entire content of chapter 11. So when an object is in equilibrium, which means that its acceleration is 0 and its angular acceleration is also 0, then the net force on that object is 0, the net torque on that object is 0. So clearly this is a situation where the torques all balance out because the object is not rotating, right? So you can equate the two torques, or you can set the sum of the torques to be equal to 0, right? So let's go ahead and do that. So clearly net torque equals 0 in this case because the object is at rest. So let's consider the directions of both of these torques. What is the direction of the torque due to mg? Which way is mg trying to rotate the beam by itself? It's trying to rotate the rod in the clockwise direction. So if mg could have its way, the rod would rotate in the clockwise direction. So mg is a clockwise torque, whereas F is a counterclockwise torque, right? F exerts a counterclockwise torque. So if we use the sign convention, you can choose whatever sign convention you like. Let's say counterclockwise is positive. That's completely arbitrary, that choice that I just made. So in that case, the torque due to F would get a positive sign, 1.5 F, and the torque due to mg would get a negative sign. And so that I'd put a minus over here. And what did we find for that torque? It was 382 Newton meters. And that would be equal to 0. The net torque is equal to 0. So you can easily solve for F from here. And if I did my arithmetic correctly, that would be 255 newtons. Okay, that is the force F that you're applying, right? Now, there is something interesting over here. What was the weight of the object? The weight of the object the mass was 100 kgs. So the weight of the object, if you times 100 by 9.8, it's almost 1000 newtons. However, with this arrangement, you can get away with just exerting a force of 255 newtons, almost a quarter of the weight of the object. And that's enough to lift up or keep the load in equilibrium, right? So you can get away with exerting a force. So suppose you needed to lift up this load, you could easily apply a force which is much less than the weight of the object in order to lift up the object, as long as the rod doesn't break. So if you have a sturdy rod that's not going to break, you can get away with exerting a much smaller force. Right? This is called the principle of the lever. So a lever, as I mentioned on slide 9, a lever is a device consisting of a rigid rod pivoted at a fixed end. It makes it possible to produce an output force much greater than the input force. So in this example, you are exerting a force of only 255 newtons, whereas the force exerted by the rod on the object is balancing its weight. So you're getting a much greater force acting on the object than you are actually applying. So a lever is a device which allows you to multiply. It's a force multiplying device. So if you look on slide 9, there is another example of a lever there, which works in exactly the same way. So you have a rigid rod and you have a 100 kg weight on one side, and that can be balanced by a 5 kg weight on the other side, right? How is a 100 kg weight balanced by a 5 kg weight? The torque exerted by the 100 kg weight is equal to the torque exerted by the 5 kg weight. And how does the 5 kg weight have such a large torque? It's a smaller force. So how does it have a large torque? Remember that torque is force multiplied by lever arm. So the 5 kg weight has a much longer lever arm, and the 100 kg weight has a much shorter lever arm. And so the torques equal out, and you can lift up a very heavy weight by just exerting a small weight on one side. So this sentence over here is a list of my favorite fraternities and sororities on campus. I'm just kidding. I don't know anything about fraternities or sororities. But this is actually a sentence in the Greek language by Archimedes. And if you have a little bit of time to kill, I would highly recommend taking a look at this website. Archimedes was one of those insanely brilliant people. He was one of the people who really thought about the principle of the lever and realized how powerful it is. He built many insanely clever devices using the principle of the lever, and he would say this thing, which is that Greek sentence that give me a place to stand and I will move the earth. So he really believed in the power of the lever, and so it's interesting. So I would recommend taking a quick look at this website. It's not for exams or anything. It's just for entertainment. Okay, and then on the next slide, I have this little poem, which I found in a book, and I find it kind of amusing. So it's based on the principle of the lever. So I'll let you take a look at that. All right, so then moving on, we have now learned what torque is and how to calculate the torque, right? All right, the next thing that we're going to study is rotational dynamics. Okay. Now, let's go back to this table which I often bring out, where we compare rotational quantities with linear quantities, and you've seen this table a couple of times by now. So we have various variables like position, and then velocity, acceleration, right? And we write down the linear variable and the angular variable. Okay, so for an object for a point mass that's going in a circle, its position would be the arc length s, and its angular position would be the theta, the angle theta that it makes, right? So this is chapter 9, beginning of chapter 9. How fast that object is moving on the circle is measured by its tangential velocity, v, and the corresponding angular variable is the angular velocity omega. How fast v is changing is measured by the tangential acceleration at, and how fast omega changes is measured by the angular acceleration alpha, right? And from chapter 9, you should know the relationships between all of these quantities. You know that s is equal to r theta, v equals r omega, a tangential equals r alpha. So that's all stuff that we've seen in chapter 9. Okay. Then we saw that inertia in the linear world is measured by mass, what is the corresponding quantity, angular quantity, that measures inertia? The answer is moment of inertia or rotational inertia, I, right? We can add one more entry to this table today. What measures, what changes the inertia of an object? Yeah, so what changes the inertia of an object? Actually, I should probably rephrase that. What causes an object to accelerate? That's probably a better way of putting it. Not what changes the inertia. What causes an object to accelerate? The answer is force in the linear world, right? What causes an angular acceleration? What gives an object an angular acceleration? The answer is torque. So the quantity in the rotational world that corresponds to force happens to be torque, as you probably guessed. Okay, now we can immediately write down an equation. Newton's second law in the rotational world is given by force equals net force equals mass times acceleration. In the angular world, what do you think the corresponding equation would be? And you can totally write it down, even if you have never studied this before, you can totally write this down just from the analogy. The answer is net torque equals I alpha. So you can write this down entirely by analogy. So it's from the analogy between the linear variables and the angular variables, the rotational form of Newton's second law, net torque equals I alpha, is completely obvious. It's also possible to rigorously prove this, but we are not going to get into the rigorous proof. So basically, in the next part of this lecture, we are going to look at applications of the rotational form of Newton's second law, net torque equals I alpha. All right, so slide 13 with the student opening a door is fully worked out on the slide, and I think you should be able to do that on your own. So I'll let you work through that problem on your own. Okay, we're going to work through the problem on slide 14. This problem is about as complicated as these problems can get. All right, so in this problem, we have this inclined plane. We have a pulley attached to it, and there's a rope that's going over the pulley, and there are two masses attached on either side of the rope, and we have to calculate the acceleration of the masses. The problem helpfully gives us the direction of the acceleration. It tells us that the mass m1 accelerates down the incline, so that is helpful. So let's see how we would find the acceleration of the system here. Now you might think that you've seen a very similar problem back in chapters 4 and 5. I think there was a problem like this in my PowerPoint which we worked out in class, and there's also a very similar problem to the one in my PowerPoint in chapter 4, I think, or maybe in chapter 5. So you have seen this exact same setup before. There is one difference between the version that we did in chapters 4 and 5 and this version, which is that the pulley has mass. So if you look back to my chapter 4 and 5 PowerPoint where we have this problem, it says that the pulley is light or massless. So there are words like that. In this problem, the pulley does have a mass, and the mass of the pulley is given. And also, the pulley also exerts a frictional torque. So there is friction in the pulley, and the pulley also has mass. So these two complications were ignored when we did the easy version of this problem back in chapter 4. All right, so most of the working of this problem is going to be identical to what we did earlier. We will just have to do a little bit more work in taking into account the mass of the pulley, right? All right, so how do we do this? We are going to do it exactly, we're going to start out exactly the same way we do Newton's second law problems, which is we identify all the forces, then we break the forces into components, apply Newton's second law. So we're going to proceed in exactly the same way. So let's start with M2 and identify all the forces that are acting on M2. So what are the forces acting on M2? Well, there is the force of gravity acting down like this. And there is a tension force which is going to act up like that. Let's call this tension T2. Right? Okay, that's the tension that's acting on M2. Why is there a tension on, where is this tension force coming from? So to remind you, any rope which is being stretched taut has a tension force because it does not like being stretched, right? So the moment you stretch the rope taut, there are forces which show up at the two ends of the rope, resisting your attempt to stretch it out, right? So there are two tension forces at two ends of the segment. So there will also be a tension force over here, right? Okay, now let's consider, and that's all the forces that are acting on M2. Let's consider M1. What are the forces acting on M1? There is the weight of M1 acting down like this, M1G. Then there is a tension force, let's call that T1, acting like that, right? And there would be a tension force on this side as well, which would also be T1. So for this segment of the rope, which is left of the pulley, it's not happy about being stretched. So there are two tension forces at the two ends of the rope, which are which show up. Okay, what other forces are acting on M1? There is the normal force, which is acting perpendicular to the incline, Fn. Okay, anything else? And that's all the forces that are acting on M2 and M1. Now we can just do our standard thing, which is we need to break the forces up into components for M1. For M2, everything is along a straight line, so we don't need to worry about that. But for M1, we need to break the forces into components. And again, this is all stuff that you've seen before. I'm not doing anything new yet. Haven't done anything new yet. So let's just consider break up the forces in this direction and also in the perpendicular direction. So the component of the weight in the perpendicular direction would be like this. So that would be M1G sine theta, if this angle is theta. And this component would be M1G cosine theta. All right. So we've broken up the forces into components here. Okay. So you might notice something that we did here that's a little bit different than what we had done before. Previously, we just assumed that the tensions on both sides of the pulley are the same. That is only true if the pulley is massless. And after I've done with this problem, I'm going to explain to you why that is true when the pulley is massless. Right? If the pulley has mass, then the tensions on either side of the pulley are going to be different, right? And that is why I've used a T1 and a T2. So so I'll just write that down. T1 and T2 mean separate tensions because pulley has mass. And I'm going to prove this point a little bit later. Okay. At the end of this problem, I'm going to show you, it's probably going to be obvious to you, but I'll also show you why the tensions would be different if the pulley has mass. Okay. All right. For now, let's just assume that the tensions are different and go from there. So let's go ahead and apply Newton's second law to M2, right? We need to do one more thing. We need to assume a sign convention. We could either, so it seems that the system is accelerating to the left, in the sense that the mass m1 is going down the incline and the mass m2 is going up the incline. So our sign convention for m1 would be down the incline is positive, and our sign convention for m2 would be up is positive. Remember that the sign conventions should always be, if you have a problem where the different parts of the system are connected and moving together, then when you choose sign conventions, you have to make sure that they're consistent with one another. So when m1 goes down the incline, m2 simultaneously goes upwards, right? So if you've chosen down the incline as positive for m1, then for m2 you have to make the choice that up is positive. All right. Now, there is another sign convention that we need to choose, which is a rotational sign convention, because the pulley is rotating, right? So there is some part of the system that's rotating. You also need a rotational sign convention. Can you tell me what is a sensible rotational sign convention to choose? Like, should we choose counterclockwise is positive, or should we choose clockwise as positive? Well, our linear sign convention is that when m1 goes down, that is the positive direction, right? So that's why m2 going up is the positive direction. What happens to the pulley? Which way does the pulley rotate when m1 goes down and m2 goes up? It clearly rotates in the counterclockwise direction. So the corresponding sign convention that we would choose is counterclockwise is positive. CCW plus phi is my shorthand for counterclockwise is positive. So I'll just quickly write these down. Our sign conventions are down the incline is positive, then up is positive for m2. So down the incline is positive for m1, up is positive for m2, and for the pulley, counterclockwise is positive for the pulley. Okay, so those are our signs, right? Okay, so now we have our signs. We've resolved all the forces into components. So now we can start applying Newton's second law. We'll start with F equals ma, and if necessary, we are going to use net torque equals I alpha, right? So let's start with F net equals ma and see how far that takes us. So for m2, net force would be, according to our sign convention, T2 minus m2g is equal to m2 times a. That's the equation for Newton's second law for m2. Okay. It looks like, what are the unknowns that we have here? So T1 and T2 are unknown, and A is what we are looking for. So it looks like we've got three unknowns, right? So we are going to need three equations to solve for three unknowns. Okay, let's see if M1 gives us a equation that we could use. So for M1, we have M1g cosine theta, that's the positive one, minus T1 is equal to m1 times a. That's the equation for m1. Okay, so we have two equations for three unknowns. So we're going to need one more equation, and let's see how we will get that. So that would come from applying Newton's second law in rotational form to the pulley. So let me just, so here's the pulley, right? Let me just draw the pulley part separately over here, so it's easy to look at. So there is one tension force acting on the pulley like this. Was that T1 or, yeah, that's T1. And there is another tension force acting on the pulley like that. Okay. And then, so these two tension forces are exerting torques on the pulley, and the friction also exerts a torque on the pulley. Fortunately, we don't need to calculate the torque exerted by friction because that's already given. All right, so we also have our sign convention that counterclockwise is positive. Okay, so let's start. So we're going to apply net torque equals I alpha is what we are applying, right? So let's calculate all the torques. So with correct signs. The torque due to Ft1, what's that going to be? So we are calculating torques about the center of the circle, center of the pulley. So let's do force multiplied by lever arm. So what is the lever arm of T1? The lever arm of T1, you would draw a line through T1 and then you would make a perpendicular from the reference point to that line. And since this is a circle, that perpendicular would just be a radius, right? So the radius is simply the lever arm. And same over here. The radius is the lever arm for T2 as well. So the torque due to T1 is going to be T1 times R. That's a clockwise torque, a counterclockwise torque, sorry, because T1 is trying to rotate the pulley in the counterclockwise direction. What about T2? The torque due to T2 is going to be clockwise, T2 times R, clockwise, so we give it a negative sign according to our sign convention. All right. Now, there is also a torque due to friction which we don't need to calculate, but in order to put it in our equation, we need to decide whether it's a clockwise torque or a counterclockwise torque. Let's try to decide that. So we know that the system is accelerating in the direction of the arrow down the incline. So as indicated by this arrow. So that means the pulley would be accelerating, would have a rotational acceleration in the counterclockwise direction, right? And so you know that torque, frictional torque, will never help the motion. It will always oppose the motion. So the frictional torque has to be in the clockwise direction, right? And so it gets a negative sign. So minus tau friction, and that is the net torque. This is our net torque, right? And now we have to set this equal to I alpha. And that's our third equation that we get for from Newton's second law. We had to apply Newton's second law in rotational form to get one more equation, right? Now, you might say that, okay, there are three unknowns for A, T1, and T2, but it looks like I've got a new unknown alpha. So what do I do with that? Well, when the pulley is rotating, so there is a subtle argument here, which you probably encountered in chapter 9 while doing the problems. So A is the acceleration of the two masses, right? Which means it's also the acceleration of the rope, right? Now the rope is in touch with the pulley and the rope is not slipping. So that means A is also the tangential acceleration of any point on the rim of the pulley, right? And so we already know the relationship between tangential acceleration and angular acceleration. What is that relationship? A tangential is equal to R alpha, right? So from there we can solve for the angular acceleration alpha, as alpha is equal to A tangential divided by R. So we can use the fact that alpha is equal to A tangential divided by R, because A tangential is just going to be the acceleration of the masses and the rope. Okay, so I hope you understand why the acceleration of the rope will be the tangential acceleration of the pulley. I'll just explain it one more time. The rope is moving with an acceleration, right? The rope is moving with an acceleration A. So that means every point on that rope has that same acceleration. So that means points on the rim of the pulley also have that same acceleration. And so A is nothing but the tangential acceleration of the pulley, right? And so the relationship between tangential acceleration and angular acceleration, which we learned back in chapter 9, was A tangential divided by R, so is alpha. And so from there we can just get the relationship between alpha and A. A tangential is just A here, so alpha is equal to A divided by R. We can plug that into this equation and get rid of the alpha. So T1R minus T2R minus tau F is equal to IA divided by R. Okay, so this is our third equation. And the other two equations we got for our two unknowns were, this is equation 1 and this is equation 2. I'll just write them over here. T2 minus M2G is equal to M2A. And the other one was M1G cosine theta minus T1 is equal to M1A. So this was equation 1 and this is equation 2. Okay, so we have three equations for three unknowns, T1, T2, and A, right? So the physics part of this problem is done. So the physics has done its job and given us three equations for our three unknowns. Now it's just a matter of algebraically solving these equations and finding the unknowns. Can you think of a very quick way of getting the A right away typically simultaneous equations with three unknowns are very, very tedious and can be a whole page of algebra. But can you think of a very, very quick way to get A? One trick which we have used in the past is adding up the left sides of the equations and adding up the right sides of the equations. And that cancels out a few things. But it seems like that trick is not going to work now, simply because we have a minus T1 here and a plus T1R here. So that's not going to cancel out T1, right? So T1R is not going to cancel out T1, and T2R is not going to cancel out T2. So at first you might think that the method of adding up the equations to get rid of certain variables is not going to work. However, you can easily get around that problem if you divide equation 3 by R, right? So we are going to do equation 3 divided by R. What does that give us? That gives us T1 minus T2 minus tau F divided by R is equal to IA divided by R square, right? And this, let's call this equation 4. So notice that equation 4 doesn't have the problem that equation 3 had, which is that the variables T1 and T2 were multiplied by R. We got rid of that problem. So now we can add equations 1, 2, and 4. And what does that give us? So if you add equations 1 and 2 and 4, then the T1 and the T2 cancel out, and you're left with M1G cosine theta minus M2G minus tau friction divided by R is equal to M1 plus M2 plus I divided by R square multiplied by A. And so you have numerical values for everything on the left side. You have numerical values for everything on the right side except for the A. And so you can just easily solve for A from here and get the answer. And so that is how you would do this problem. So everything is given. The radius of the pulley is given and the mass of the pulley is given. You can treat the pulley as a cylinder or a disc. And so the eye of the pulley would simply be 1/2 mr square. You can use that formula. In fact, we might as well just plug that in and do one more step. So M1G cosine theta minus, let's get rid of this, M1G cosine theta minus M2G minus tau friction divided by R is equal to M1 plus M2 plus 1/2 mr square divided by R square. So that's 1/2 capital M. Capital M is the mass of the pulley. And capital R is the radius of the pulley. So 1/2 m times a. And now you can just solve for a. All right, so please make sure that you understand this problem clearly. So this problem, most of this problem we've already done before when we worked out the same problem, the simpler version of the problem in chapters 4 and 5. The only complication here was the pulley, for which we had to apply Newton's second law in rotational form. Okay, now let me just clarify one more thing. So we're done with this problem. Now suppose you have a pulley like this, and there is a tension force T1 going this way, and another tension force, did we call this T1 or T2? It doesn't really matter. Yeah, so that one was T1 and this one is T2. The radius of the pulley is R. Okay, ignore the friction of the pulley for now, just to make things simple. So what is Newton's second law for the pulley? So it's going to be T1R minus T2R. That's the net torque, and we are ignoring the frictional torque, with, just to make this simple, is equal to I alpha. Let's plug in the I for a pulley. It's 1/2 mr squared. So T1R minus T2R is equal to 1/2 mr squared times alpha. Actually, let me just keep the friction. Yeah, why not? Let's just keep the friction. Oops. So let's just go back to the same equation that we had. So minus tau friction is equal to I alpha minus tau friction is equal to, all I'm doing in the second step is just plugging in the I for the pulley, 1/2 mr squared times alpha. So this is the equation for the pulley when it has both mass and friction, right? All right, now suppose the pulley is massless and frictionless. Then what happens? Then this right hand side is 0, right? And the friction term goes away. And what are you left with? T1R minus T2R is equal to 0. What does that tell you? T1 is equal to T2. So the tensions on the two sides are going to be the same when the pulley is massless and frictionless, right? And that is why way back in chapters 4 and 5, we just assumed that the tension on either side of the pulley was the same, because the problem told us that the pulley is massless and frictionless. Okay. So the problem on the next slide is an easier version of this. You just have one rope on one side of the pulley. So I'll let you try this on your own. And in the next video, we are going to talk about the next chapter, which is rigid objects rotating.